Good evening, everybody. I'm Daniel Jarmello, and today I'll be doing project number 2, doing the Excel and data tabulation and analysis part. My friend Julian already did the ANSYS and he exported the data right after the results. You can just go to export depending on the result you want, like your contours or your velocity relative to your boundary layer thickness. And you just press export and you export the values onto a note and then you copy and paste them here. That's how we got here, and I organized it a little bit, obviously. Here are my initial conditions given. My velocity is 2 meters per second, my rho is 1.2, my kinetic viscosity, and my length is 1 meter of the whole plate. And then we can just start answering by part B. It asks us to plot the velocity profile at x is equal to 25 centimeters, 50 centimeters, and 75 centimeters. So I'm going to do that actually by just gonna insert a nice graph. I'm going to select my data. And my first piece of data is going to be x is equal to 0.25 meters. And the reason I'm only going to do my x values up until the 2.06 is because this is essentially the velocity, which is a constant actual velocity over the flat plate. But the only reason you see it increasing is because the free stream tends to accelerate a little bit due to the nozzle effect that the boundary layer creates, because the actual nominal uniform and steady velocity is 2 meters. So here you can just see how the boundary layer develops as this develops, and then as it reaches just 2 meters, it should just be it would go to infinity because the boundary layer would be fully developed at that velocity. But since we're early on in the x, remember it's going over the x, we're not going to see a full developed region yet. Hence this. Let's grab my y values. Boundary layer thickness. Okay. Let's go ahead and add our x equal to 0.5. And then as you can see, as we go on with our x, as we increase it, we are seeing the increase in our boundary layer. That's exactly what we want to see because up until a certain point of x to where we have the full uniform velocity is when our boundary layer will converge with the free stream. Okay, okay. And then as you can see here, as you go deeper or farther down the flat plate, you do see an increase in that boundary layer. Up until it hits 2 meters, and I can show you this, is that it'll just eventually go to zero point 0.5, not because it's actually that size, but because we're just graphing it by zero point 0.5 by zero point 0.5 meter. But this is our real boundary layer at that point, our boundary layer thickness at that point. At this max velocity, even though it is really 2, that max velocity is only hit over 2 because of the effects of the nozzle due to the boundary layer. So let's add some axis titles. And then we can call this for the first part, velocity profile. Velocity profiles. And then this down here, it's going to be in meters per second. And this is just going to be in meters. Very nice. Okay. Now, the second problem asks us to get the boundary layer thickness values using the velocity profiles obtained from Fluent. Excuse me. Okay. Compare with theoretical ones in table. Interesting. Okay. What are the theoretical ones? Well, here we're going to calculate them based on just values that we were given, on the singular values that we were given. So to find Reynolds number, I'm going to use the equation of velocity times characteristic length over viscosity, kinematic viscosity is our Reynolds number. It's a variation of it actually. And so here we'll begin by doing our velocity times our length, which is actually going to be at the length that we're taking it at, divided by our kinematic viscosity. That's going to be our Reynolds number. And this equation is going to be the same. Hold on 1 second. Sorry. Exit this. We'll get this, but instead of B3, it's gonna be F. Okay, and then we're gonna do the same thing. Very nice. Then once we have our Reynolds number, we can go ahead and calculate our boundary layer thickness using the equation that our characteristic length times 5 over the square root of Reynolds number is our boundary layer thickness. So let's go ahead and do that. So we're gonna have 5 times characteristic length divided by square root of our Reynolds number. One more. Very nice. And then we can see here how they start to compare. Close, but not really that close if you look at the real max boundary layer. But if you go to 2.06, it's actually very close. So theory is coming in pretty well there. Let's go ahead and copy that so we can reuse it. So instead of B3, we're going to do 0.5 instead of C6. Reynolds number here. Very nice. 0.79, 0.0079, and here we at 2, we have 0.081. So very close actually. Our values are indeed very close. And then we'll go to our B3. That's going to be our length of 7.5 at this one. Our Reynolds number at this one at 0.75. Press enter, 0.96. And here we have, wow, it's extremely close. It's barely under. Very nice. And then we can actually compare these by just making a quick little chart based off of these x values. I'm going to make it equals 0.25 equals 0.5 equals 0.75. And my y values right here. I'm going to have y. Let's not call them y1. Let's call these answers. And then let's call these theory. And then we're going to have our ANSYS numbers are going to be equal to right here. Well, as a matter of the fact, we should just compare it to our actual 2 meters because this is obviously the real scenario, but this is based off of 2 meters, the boundary layer. We're also going to compare it to the ANSYS 2 meters, right? So I guess we'll go here with 2.01, just barely off, but this should work. There you go. This is going to be equal to the 0.5 at 2, and this is going to be equal at 7.5. Whoops. Now my theory is going to be equal to 0.25 there and there. And then based off of this, I can make a very nice chart that looks like this. That easily demonstrates the actual, whoops, ANSYS versus theory. And then we can actually add some axis titles to that. This would be in meters. Meters. And this would actually be in meters as well. Whoops. Whoops. Meters. Very nice. So yeah, so we can see here that they're almost the same. The ANSYS is just a little bit higher than the actual theory. But I would say the margin of error is less than 1% here. And so based on that, I would say theory is actually more than enough to actually calculate these values. Now moving on, our second question tells us to plot the wall shear stress and skin friction coefficient along the flat plate using Fluent. Compare with theoretical ones on the same graph. All right. What's the theoretical one? So we have our shear stress, our pressure, our skin friction based on the x, and then our skin friction coefficient. And now we must do let's actually move this out of the Okay. So let's begin with our theoretic shear stress. What's our shear stress? Our shear stress is going to be mu du dy, but we can also calculate it by doing another equation where it's square root of mu, square root of rho, square root of u over the x that we're on. So let's actually write this equation out. This is going to be equal to, let's see, equal to parentheses 0.332 times mu, which is going to be our viscosity, to the power of 1 over 2. Whoops. I can just make it like this. Of 1 over 2 times rho of 1.2. Whoops. 2 to the power of 1 over 2. Our mu is actually going to stay the same, so we need to make sure we add one of these, if you know, times our u velocity, which is going to be changing. I'm sorry, that's not our u velocity, that's actually our force, I believe. So right here, yeah, to the power of 3 over 2. And then we're going to close these parentheses. And we're going to divide that by our x value to the power of 1 over 2. And then we're going to go ahead and drag that down. So these should not be 0. x5. Okay, 1.2. N4. I see, so still did change it. It's not supposed to though. Is it like this? No. I mean, we can always just do this number. Control C it. And go in here. Control V. Give it its own pair of parentheses. And that's obviously going to be 0, but then we'll be able to actually pull it down. One second. One second. Actually, I'm mistaken. Yeah, 1 second here, ladies and gentlemen. 1/2, okay. I can write this much easier, actually. It's gonna be equal to 0.332 times square root, and this is gonna be double parentheses, and it's gonna be 1.2 times mu, which is, I'm gonna go like this, times velocity cubed, which is 2 cubed. And these will go like that. 2 cubed, close these parentheses, and that's going to be divided by our characteristic length. One second. Um, let's see. Over M3. There you go. What's the typo? Yeah, sure. Fix it then. Okay, there you go. As you can see, the values are a little off, but they're not so much off, I would say. Pascals. Our shear stress in pascals. This is going to be our shear stress in pascals as well. Um, Obviously, if our x is 0, it's going to be 0. So, now we'll do the skin friction. And the skin friction is going to be equal to, it's going to be equal to 0.664 divided by square root of Reynolds number with respect to x. So let's just do this. And this Reynolds number with respect to x is going to be the same thing I did back here. Velocity times length over v. Our velocity is going to be 2 meters times our characteristic length. This is going to be equal to 2 times characteristic length over, I believe, this number. Yes. Our viscosity. And then with this, we'll actually go ahead and drag it all the way down so we can use it. Very nice. And so now, this will be that, which means that we'll drag this down as well. There you go. Then you can see that they're almost similar, but not too similar actually. And then we can actually demonstrate these on a graph. Plot the using, okay, perfect. So now we're gonna plot these um, like this. I wonder if I plot both of these on the same graph. So let's make this one graph. I like this actually. Let's see if we can edit this graph a little bit though. So let's see if this makes sense. our series 1, 2, horizontals from 0, correct. I, yeah, I mean, that looks pretty right. And then the blue is going to start at about zero point 0.7 as X goes on. And they're going to converge actually later on. So as you move the equation further down, they eventually do converge, which is pretty interesting. So it is still pretty accurate. It doesn't look accurate, but it definitely converges, which makes it not too bad. And then we'll just call this one the wall shear stress. Wall shear stress, comma, ANSYS versus theory. Theory. And then our axis title, shear stress is measured in pascals. Pascals, and then down here is just our x values in meters. Our legend. Actually, yeah, let's do this. So series 1, I'm gonna call this ANSYS. ANSYS. And then series 2, we'll call theory. Very nice. Put that right there. We should actually do this for this as well. There you go. Very nice. Okay. And then lastly, we'll do our skin friction here, the same thing. Insert recommended. I like this one as well. Go here, access titles, legend. And then, yeah, this also shows the same thing. However, on the left, skin friction is measured in newtons, I believe. Newtons. Obviously, this is from 0 to 1 meters. I believe that makes sense. Put that one right here. Very nice. Okay. Get the drag coefficient for the flat plate using Fluent. Compare with theoretical one in table. Okay, let's get the drag coefficient. Okay, where do we begin? Drag coefficient and ANSYS. It's going to be based on... Well, first we can just do our theory, right? So let's do drag. So this is going to be our 1.328 divided by the square root of RE length, Reynolds number at 1. Okay, let's just double check. U53 is our Reynolds number, and that Reynolds number is going to be, when we double check it, it's going to be the velocity times the length of Q53 over V, so that is correct. So this is our drag coefficient, our theoretical drag coefficient. And then we'll have our drag in newtons. So we have that ANSYS gives us this. Oops, I'll just type it in actually. Our newtons. And this is gonna be 0.0153, and that's in newtons, right? Okay, and then obviously our coefficient of drag based on the drag force, of force drag, right? It's just going to be equal to this Newton number divided by 1/2 times rho times 2 squared. Let's double check. Times 8 divided by, so here we have our one drag coefficient using theory, other drag coefficient using ANSYS. This one's about 50% off. Um, Let me actually write this. Let me to format this. I'm gonna do it like this. Actually, no, I'll do that. Put it here. Move these three down, and then I'll make this one the theory, and this one the ANSYS. This is just the coefficient of drag, and then I can make this into just a, I guess, a simple chart, I suppose. And then here you have it. Here's all the graphs that we need, and I believe that's the last question. And thank you so much for watching.